Just double check. Yeah. It's working. Yes. Okay. All right. Hey guys, welcome back to week 3 of this course. And your first block test is coming up, but it's online. It's in week 4. So if you didn't know about that, surprise. But it'll be on the first 3 weeks, I believe, of content. Yeah. Basically, today we're going to be talking about strain, and it's going to be fairly similar to the last 2 weeks in that it's fairly like fundamental, similar to stress, to the mechanics of solids, and also we'll be talking about the Mohr circle rotation crap again, basically. So yeah. Okay, so in terms of the course content and where we're at, we've done geometric properties in week 1, and we did stress last week, and now we're going to be talking about strain. Okay, so I believe these 3 weeks is what your first block test will be testing on, and your first block test is next week. All right. Just looking ahead a little bit, week 4, there's actually quite a bit to talk about. There's squeezed a lot into this course in week 4, so it'll be material properties, axial loading, and methods of structural analysis. Yeah, I mean, I'll talk about that more next week because it's not important for the moment, but just keep that in mind. But yeah, I do think this course gets a lot more fun after this week. So if you're kind of sick of the Mohr circle, then that's kind of fair enough. But trust me, it does get a bit better. All right. Yeah. So just a snip from your middle page, right? In case you haven't seen it. So progress quiz online, week 4, 6 p.m. And this one's online, right? So you can do it from anywhere. You can do it from home, whatever. And then week 7, we have a midterm exam basically, and it's in person, but it's not during this workshop. It's at 6 p.m. I'm not exactly sure the details of where it is, but I think Alina will let you know pretty soon. So just keep in mind those are like your 2 kind of tests before your final, right? You have to deal with. Okay. Does anyone have any questions about that? Okay. So, yeah, that's just what is coming up. In terms of this week, we are talking about strain. You kind of have to excuse these notes a little bit because, like, I try to fit everything into one page for this particular week because I don't find it that beneficial to just memorize a bunch of formulas. Like, it's better. Like this week, I've included 4 examples. It's better to see how the formulas are applied to understand this content than just see all the formulas laid out, because some of these are derivations and stuff as well. So this is like a compressed version of what you see in the lecture slides, right, for the formulas. But I will briefly run through them. So basically, if you imagine your solid element, right, similar to last week, and you're stretching it, basically, so say in tension, it's going to elongate. So if the original length of that element was LO, right, it's going to extend by some amount called, let's call it delta L, right? Sometimes you see this as E, okay, but it's the same thing. So delta L and E. E stands for elongation, right? Same thing, right? And then dividing that by the original length, or sometimes it's called L, right? That's what strain is, okay? That's what axial strain is. So average axial strain, I should say. So what you'll find is that this is unitless, right? So if this is in millimeters and this is in millimeters, strain is unitless, basically. Okay. Another thing to keep in mind is elastic modulus, but I actually don't think we talk about that too much here. Okay, we'll talk about that next week, all right? That's a material property, basically. We'll talk about the material curves of, we'll talk about material curves basically next week. Okay, so, and we'll also talk about next week Poisson ratio. So if you imagine like, I had Play-Doh, but I didn't bring it. But if you imagine like Play-Doh, right, and I'm like stretching the Play-Doh, it gets thinner, like it starts necking, like as I'm pulling it, right? So that's like a pretty exaggerated way to like imagine Poisson ratio. So the idea is that as you're elongating something, right, that longitudinal direction, it kind of shrinks in the radial direction, right? Just keep in mind. Okay. Yep. Derivations. Okay. Shear strain. So, whatever. I'll explain small angular changes in a bit, but what you have to know about shear strain is it's also this idea of like something in millimeters divided by millimeters, right? But it's in a different kind of direction. So it's like you're dividing it as like a perpendicular thing. So instead of longitudinal, like that's the stretch divided by that's the length. This time you're doing, I might highlight it. This time you're doing the elongation that way, and then the perpendicular dimension. Does that kind of make sense? So if you have like a stack of papers or something, right, and then like you push it at the top, well, yeah, maybe you get your hand, and then like you're sliding it that way, right? It's gonna shear, and essentially that like kind of the I don't know what the word is there, but yeah, that basically like shear deformation in that direction divided by that the height of the stack of papers, right? That's your shear strain. Okay. And then there's also an equivalent thing to the elastic modulus, but it's the shear modulus, which we'll talk about next week. Okay, so that's also a material property, basically. That's the shear stress divided by the shear strain. Okay, so these are all a bunch of formulas. All right, and shear strain on an element, you have to basically draw it out on an XY plane as like kind of a rhombus, I guess. So the shear strain is this portion and this portion added up. Yep. And basically it'll be positive if your shape is narrowing in angle, like that. So that's a positive shear strain if your angle becomes more acute, right? And if it becomes more obtuse, then that's a negative shear strain. Okay, so that's, again, this is easier to see like when I show you the examples, right? But the important thing is that you're going to be mapping these in radians rather than degrees. So I'll tell you how to like switch that over on your calculator when we get up to that as well. But the reason for that is basically radians are unitless. You can think of them as like unitless, right? Similar to how when you divide millimeters by millimeters to get axial strain, you get something unitless. So to map these against each other on a Mohr circle, you have to have two unitless axes, right? Okay. That's like the overall rundown of these formulas. Does anyone have any questions about that? Okay, cool. All right, let's start with something pretty basic. So if you imagine like a rod, okay, and it's pinned at the bottom to the ground, right? So like a pin support kind of thing, and there's like a cable that is suspending it at the top, and you pull it to the right, as drawn in this diagram. If you're told that there's a 5-degree angle change, right, from the original like completely vertical shape of this rod to when it moved a bit. I'm just gonna pull up my notes. Right? Yeah, and now it's like tilted a little bit, and it's tilted 5 degrees. Okay. It's basically asking you find the normal strain in AB. Right. So AB is the cable, basically. I might highlight this. So this was the original cable length in orange, and this is the final one in green. Okay. So this like might be one application of strain, basically, right? So if I highlight that again, except over here where I've drawn like some triangles. So the original is in orange, and the final shape's in green. Okay. So you're given some dimensions, right? And if we use a good friend Pythagoras' theorem, we have 800 in the height, and then 600 between, I guess, like where the cable starts and where the rod starts on the ground, right? That's how you can find the original length, right? Because you just use Pythagoras theorem. Now for the final shape, basically you can use Pythagoras again, but first you have to get these additional dimensions, right? So let's call them A and B. So just keep in mind, right? I'm gonna do like a little call out thing for that one. In this problem, we've assumed that our rod hasn't strained at all, like it hasn't changed in length. So that kind of diagonal red thing that I've drawn there is still 800 mil, like that, right? Okay. So what's this dimension A and this dimension B? Okay. So if you remember your trigonometry, right? A is basically on the adjacent side, right, of this angle. So we're going to be using cosine, and then B is on the opposite side, so we'll be using sine for that one. Okay. So A is 796.96 millimeters, and B is 69.72 millimeters. Okay. And keep in mind that you have to add on B to 600 to get the entire length. So we want the length from here to here, right? So we're going to add these together. So doing that, right, and we substitute all the numbers in, gives us 1040.99 mil. Okay. Cool. And basically, if we want the change in length, right, like how much has our cable, right, our cable AB, how much is it stretched, right? We get the final length and minus off the original length. Okay. So remember the original length was 1000, and the final length is 1040.99, right? So the difference is 40.99. Okay. All right. So that's what we sub into here, our strain formula, and for LO, yeah, that was just 1000, wasn't it? So our final answer is this, basically. And it's unitless, okay? So no need to write millimeters for strain. Yeah, so if you guys remember from 1300, this might look pretty similar to when you looked at springs. Yeah, because we have like this. And remember your spring, yep, so your spring constant was in newtons per millimeter, and it's to do with how much force resistance it has to stretch it 1 mil or whatever, or maybe it was in meters, but anyway, this is the amount of stretching that's happening, basically. I don't think that was a good comparison to illustrate my point, but yeah, hopefully you can draw some comparisons and see how this kind of all fits in. You can think of the cable as like a spring, basically, right? Because the cable can like elongate, basically. Okay. All right. So I know a few of you guys just got here. That's the attendance form, but also I bring this up because if you need my notes QR code, scan it out, because there's a chance that I go too quick and then you don't see like the working out before I like move on. So I'll just give you a few seconds to scan those if you need. Okay. All right. So that's the first example. Okay, the second example, we have this rectangular shape, right? And then we're told that it stretches into a shape like this, okay? This kind of rhombus thing, but it's not quite a rhombus. It's quadrilateral because you can see that this shape, right? It has a different amount of stretching in the x direction versus the y direction, right? As you can see here. So, question asked from us, given the geometry of deformation of the shape, right? Find the strain, the AC strain. So AC strain is this one, this diagonal, and find the BD strain, which is that diagonal, right? And also find the strain at A and the strain at D, okay? So the strain at A is here, right? So how much does this angle strain? And how much does this angle strain? Okay. So here's how we're gonna do it. All right, so the first thing is we do something similar to what we did with our cable before, right? So remember our cable, I'm just gonna go back to the previous example. So our cable, you can think of it like a spring, right? So it got longer. You can kind of think of these diagonals as like springs, right? So how much does our spring stretch and squash? Okay. So we can find the final length of our AC spring by essentially, we utilize Pythagoras again here, for example. Okay. So let's focus on the purple one, right? So in this direction, it's basically stretched 9 mil, right? And so the reason I got that is because it's 400 plus 9, right? So that horizontal dimension is 409, okay? And in the vertical direction, you can see it's stretched 11 mil, right? So that's 300 vertically, and then 11 is how much it's stretched, right? Okay. So that's the purple one. If I get a different color real quick, this green one, right, which is for the other diagonal from B to D, you can see that it's gotten smaller, but it's like, okay, how much smaller has it gotten? This original dimension, remember, was 400 in the horizontal direction. So this was originally 400, okay? It's basically shrunk by 5 on the left here, but also on the right, it's gained 3 mil. Yeah. Up and down, we've got, it was originally 300, and we have basically gained and shrunk 4 mil. Okay, so it's moved up just 4 mil. The top and the bottom have just shifted 4 mil. Does that make sense? Okay, so concentrating again on our original diagonal, right, which is from A to C. Looking at the numbers from the orange dimensions, right, we can do 409 plus 311, 409 squared plus 311 squared, square root the whole thing, Pythagoras, and we get this, okay? Yeah? Okay, what about for the other diagonal, which is from B to D? For that one, we look at the green dimensions, and we can see it was, what's that? 398 squared plus 300 squared. Okay. So that one is 498.40 mil. Okay, so you can see the purple spring stretched and the blue spring shrunk. Okay, cool. So change in length, right, was the final length of the purple one minus its original length, which is 500 because Pythagoras theorem. So if it's like 3, 4, this one has to be 5, so this diagonal has to be 500. We get a strain of 0.0276 right? Well, I mean both of these. It's going that way, sorry. But AC was the purple one, sorry. So that was the purple one. That was the blue one. Okay. The blue one was 498.40 minus 500 divided by 500. Okay. So this one, since it shrunk, we have a negative strain. Okay. So basically, if we have a positive strain, it's going to correspond to elongation, right? If we have a negative strain, it's going to correspond to like a squashing, right? Makes sense? Right. Does anyone have any questions so far? Because now we're going to be talking about the shear strain. That's the axial strain. Okay, so for the shear strain, we're looking at gamma A, right? And gamma A is basically made up of these two angles, okay? So where does that come from? If you look at these formulas again, let me just delete all the fluff that I added. Right, so just concentrating on this part here. Right. What's this letter? Gamma, sorry. Gamma xy is equal to gamma xy divided by 2 plus gamma xy divided by 2. So we're collecting these two shear strains, and that's what gives us the shears, overall shear strain. Okay, so going back to this and how that applies, basically if we get this gamma 1, which is highlighted in red, okay, and we get this gamma 2, which is highlighted in blue, we add them together, that's what's going to give us the shear strain at A, okay? The shear strain at A is both those components added together. Okay, so how are we going to do that? If we get pi on 2, which is 90 degrees, and we subtract off that angle, right, this angle here, then we'll get it, basically. Oops. That's one way to do it. The other way is just adding those two angles together, which is the way that we'll do it, I guess. So if we do tan, so here, the amount that it's changed that way is 5 mil, right? And then the amount that it's changed, sorry, it's not a good example. I should draw it very thick. I might draw it in red. There we go. So that dimension is 5, and that dimension is 304, right? So if we do tan to the minus 1, we can get the angle, right? Because theta tan to the minus 1 rise over run. Okay. To get the angle, you do tan inverse of your rise over run, if that makes sense. So the rise is 5 mil, and the run is 304. 304, yeah. Okay. So that gives us this, but you have to make sure that this is in radians, because by default, I think your calculator uses degrees, right? So I'll just quickly explain how to change that over. I know most of you guys already know how to do that, but just as a refresher. So if you press shift on your calculator and you press this button, it's gonna bring you to the setup, and then you can click 4 after that. So step 1, click shift. Step 2, you click setup, and step 3, you click 4. So 4 brings you to radians. And then similarly, if you want to swap back to degrees, you just click 3 instead, and then that brings you to degrees. Yeah? Okay. So we want these in radians, basically, okay? Because they're unitless. All right, so similarly, we do the rise of a run here. Okay, so 4 is the rise, and, sorry, didn't draw that correctly. From here. So 4 is the rise, and 403 is the run. Okay, so we do tan inverse rise of a run. That gives us 0.0099 in radians, yeah? Okay, if we add those together, we get A, basically. So this is equal to that plus that. So we just add these two together. It gives us 0.0264 in radians. Cool. All right, I'm going to quickly talk about the small angles rule, which I briefly mentioned up here in the formulas. It's called, for small angle changes, tan gamma is approximately equal to gamma. Okay, so why is that? Modeling this on Desmos, so just as an example, I've taken this one. So gamma 1, right, was 0.0164, okay? So basically what I'm trying to say is if I do tan inverse 5 over 304, and you punch it in the calculator, you're gonna get 0.0164, assuming you're in radians, right? That's the answer that you get. But if you just type this on your calculator as well, without the tan, you're gonna get a very similar number, okay? It's because for small enough angles, which is like for the case of strain, because straining something will not really change this angle very much. It won't be a big angle, basically, is what I'm trying to say. But yeah, so basically they're very similar numbers. You'll get something that's also pretty much this if you round it to 4 decimal places, whatever. So looking at this Desmos graph, right, we're in the region which is like here, okay, for x. Yeah, and so if you model it, they start to diverge at a certain point. It's like, okay, at what point does it diverge? That's kind of like subjective, but basically if your number is like less than, let's say, 0.2, like you're completely fine, basically. These numbers are gonna be so similar that to like, 3 or 4 decimal places, they'll be the same. Does that make sense? So that's the small angle rule. Okay, so I've actually gotten through, sorry, okay, just finishing off the question. The other part of the question was asking, give us gamma D, right? So gamma D is what's the strain in this corner? And the strain in this corner is basically these two shear strains added together. So we know that the first one's the same because the Z angle formula, or the Z angle rule, is saying that if this angle and this angle are like this, this parallel, then they're equal, basically, right? So we can reuse gamma 1 from the first part. Gamma 3 is what we have to work out, and you just do the rise over run. Okay. And when you add these together, you get, I don't know why I did all this like random shit, but basically if you just add those together, you get gamma D. Okay. The other thing to mention, I think the reason I did that actually is because to prove that it's negative. Okay. So this has got us the magnitude. So if we add these together, you just get the magnitude, right? But do you remember how before I said if your angle goes from, say it's right angle, right, and it becomes obtuse, right, you get a negative shear strain, right? So that was like the sign convention. That's this one, okay? So it's widening, except for our case, remember it looked like that, okay? And we were observing from this top left corner, right? So the angle's getting more obtuse. Are people following? I don't know. Okay, cool. Anyway, point is, it gives you a negative shear strain, right? So you can just do it from adding these together, but then you make it negative because you know that a more obtuse angle makes it negative. Or you can do all this derivation crap that I did, basically, to prove it. All right. Cool. Actually, I'm progressing faster in this lesson than I thought. I've got 2 more examples, but we can do that after the break. So I'll give you a break now. Yeah, 5-10 minutes. Come up the front if you have questions. Cool.
Agents.
What are your roles? Oh yeah, back in the day. It was ages ago. It was 2 years ago. Are you finding this concept? You guess better. Over the street.
You guys are still boys.
Well, like in the first 2 years, like that's what you're exposed to. Figure out layers of it. Get exposed to stuff. 30 years is
Or you can get a drink
One of those moving trucks. Like the car. What are you doing? Stop. Anyway, so I'm at the satellites and I'm let's run all right together. I just go to the straight down.
That's not thinking.
I was the last one.
That's just you, right? That's
No one was behind me, okay? No one was behind me. We're all sitting there patiently waiting to go and turn left, okay? And then
yeah, that's what I was used to do. Then our voice was like, and then I gotta pull my laptop. I gotta go. Once you're an expert, yeah.
And then he says, I'm not listening, I'm not moving. I'm freaking sped down the road, in a school zone. Sped down the road, and then cutting from the street, trying to cut it off. Mind you, I'm gonna cut him later.
Came with a good TV, but they had a mask on.
Actually, wait,
They told him to take it off and he had a full.
sorry, I'm sorry.
Yes, I know. Your school's on you about like fades. Like in the yard.
It was 8 o'clock. What are you doing speeding at 8 o'clock?
And then they changed the rule to 0
Yeah, but like, wow.
But it's okay
Yep.
if your haircut was actually like Gucci.
So somehow
So like, if you got a face, but it's a shit face.
So you're stuck on it.
There you go.
I just want to put a sign like a
Oh, you need a good
on my
bulb.
car, right, that says acceleration on the right and just blink it whenever.
Bro, I could just do whatever. No, my uniform will assist me. That's where you get through my
We had to go along.
my school, my state changed now because they got rid of my school, so like which one they choose.
Although what's just complex with it feels like coming right off. I think some schools now want to put ties and shit.
Yeah, we got rid of ties. So do you know what they did? You still have the
Dismantle.
and what they did was they added the clips.
I guess. Alright. Sorry, I know you guys are having fun chatting, but we will just continue the workshop and yeah, and then you guys can kind of like leave early if I finish early. So I realized what I was trying to say with the spring thing, right? So I brought up this formula, and from 1300, you might remember this part, right? So the delta x, right? So for a spring, right? Yeah, like its material property is that it has a spring stiffness of, and it's in like newtons per millimeter, right? What I was trying to say is that its displacement, right? So if that's like its original x length or whatever, its displacement, right, was delta x. So this is very similar to what you're kind of working out here, if that makes sense, for axial strain. That's kind of the analogy I was trying to draw. Anyway, so yeah, okay, our good friend Mohr circle is going to pop back up. So we've got strain transformation now. These formulas should look pretty similar. In fact, I just copy pasted from like my previous week's notes and just changed a little bit, right? But basically from last week, what we considered as sigma x is now this epsilon x, right? The y is the y equivalent, and gamma, oh sorry, other way around. What was this one again? I'm drawing a blank. Oh, it's tau, yeah, sorry. So tau xy is now gamma xy on 2. So that's where it's different, okay? So just keep this in mind. It's not a 1-to-1 because it's divided by 2. So if you remember, it's because, like, if you were to rotate your stress element before, right, you only had this like angle change, right? So say you're rotating a stress element, but now we're doing it twice. Does that make sense? Kind of like rotating that way plus like that way. Do you get what I'm saying? Because you're like kind of squashing that shape in like 2 ways, but you're doing half the amount of like squashing. Okay, so basically the point is all these formulas, like they work out to just be the same, except that you're using gamma xy on 2 instead of what you'd expect, which is gamma xy. Okay. So anything different? I think before this formula looked something like this. It would have been tau xy on 2, I think. Or was it 2 at the top? I think it was 2 at the top. Yeah. I have to double check that, but it's one way or the other, but there was a 2 at some point, right? But you can see that that's cancelled out because we have gamma xy is like divided by 2. Do you know what I mean? Okay. Yep, so that should look pretty similar. That's just the middle. So you got the Mohr circle, right? You have your principal angles, principal strains. Your biggest one is epsilon 1, your smallest one's epsilon 3, right? The middle is your average between them. So that's that and that, or in this case, if we're given values which are like x and y, you're just trying to find the middle of the circle, right, by averaging those values. And then this is your radius. So that thing's in purple. That's the radius. Okay? All right. Mohr circle, again, should look pretty similar. We're graphing it so that it's gamma xy on 2 in this axis. All right. Okay. So let's look at an example, because hopefully it should make more sense in an example. So there's a point of the surface on a structure, and the following strains are known. Okay, we have strain in the x direction is 0.001, strain in the y direction 0.002, and strain xy is 0.001. Okay, so first thing we do is we can substitute in numbers to find our principal. Oh, actually, wait. Before we do anything, all right. So just think about maybe think about this element for a second, okay? So the strain in the x direction, right? Strain in the y direction, right? The arrows are pointing away from the element because they're positive, right? And we have a certain strain, which, sorry, this is just like hard to draw. It's like that. Yeah. So let's call that gamma 1. This one's gamma, oh, actually no, that's a bad way to do it. Let's call that gamma xy on 2, gamma xy on 2, like that. And so gamma xy is 0.001. Right? So that's kind of what our strain element looks like. So if you have a shear strain that's non-zero, right? What does that imply about where this sits on a Mohr circle? Basically, if you're given that this is a non-zero number, right? So this is not equal to 0. On a Mohr circle, we know that it's not sitting here and here. Okay, because if it was principal, this thing would be 0, right? Yeah. So we already know that it's going to look like this, or like that, or whatever. You can figure it out. But yeah, so we're working with something that that's not the principal, okay, to begin with. So we have to find the angle to get to the principal axis, okay? So that's theta p, right? So how do we do that? We chuck in our formula. So that's where that's like the point, I guess, right? So that gives us -1, okay, for this whole expression, okay? What we can do is we go tan inverse -1, tan inverse -1, and oh wait, crap, what am I doing? Sorry. I skipped a step here. Basically, it's like this: tan inverse -1, like that, right? We do that on our calculator, and remember to change your calculator back to degrees for this specifically, right? So you're going to be pivoting between radians when you're doing like the shear strain, and you're trying to find like it based on a real geometric shape, and you have to do like the rise over run stuff. But if you already have that value, I would recommend changing back to degrees for when you're dealing with the Mohr circle, right? So like, yeah. If you're in degrees and you're on your calculator and you type tan inverse -1, you'll get 45 degrees, -45 rather. You divide that by 2, right? And we get that the principal, the degrees to get to the principal axis is -22.5. Okay, cool. All right, so next we find on the Mohr circle, we're looking for here and here. Okay, so the minimum and maximum axial strains. How do we do that? We do the center plus or minus the radius, so going that way or going that way, right? Subbing in these values, right? We have 0.001, 0.002, etc. Okay, and yeah, you can kind of see how these numbers are like subbing in, and we get 0.00221 and 0.000793. Okay, so that's the smaller one. That's going to go here, and this is the bigger one, so that's going to go there. So that's your Okay, so, sorry, I've been a bit inconsistent. Sometimes I call it epsilon 2, sometimes I call it epsilon 3, but same thing, right? It's the smaller one. It's a smaller value for your principal axis. Principal strain. Okay. All right. Cool. So next we're gonna find the max value. So on the Mohr circle, we want to find this thing here. This we'll call it gamma max on 2. All right. So to find that, you sub in this equation. Oh, what the fuck is that? Oh, sorry. So I thought it was like an alarm for the building. No, you're good. You're good. I thought we had to evacuate or something again. Fucking hell. All right. So yeah, basically you chuck it in this formula and you get this value. Okay. So that's over here. All right. So remember, that's telling you how much, like how to map it vertically, right? How do you map it horizontally on this Mohr circle? You can map it horizontally on this Mohr circle using this, right? The average between the 2 points, right? So if you have the average between here and here, or what we started with was here and here, right? You take the average of those, and that's where we're plotting. That's where we're going to plot it on the Mohr circle. If you know what I mean? Yeah, the middle of the circle is where you get the max shear strain. Okay. So, yeah, I mean, actually, I wrote it like this, but it's better to keep it as gamma. Oh, I guess for the sake of the question, I think they were asking what's the max shear strain, so maybe it's good to have that value there. But for the purposes of plotting onto the Mohr circle, it's probably better to leave it as like divided by 2, because that's what we're actually going to be plotting on the Mohr circle. You know what I mean? Okay. All right. So pretty much, how does this look like? So that's what I'm calling the. So what I've drawn here, this is the principal axis, and so the principal axial strains I've drawn in red. Okay. And you can see that this shape isn't like a rhombus or anything because it's the principal element, right? So at this like rotation, it doesn't have any shear strain. Okay. So what I mean by that is because it's easiest, in my opinion, to plot your principal strains first on your Mohr circle because it gives you a good like guideline or framework on how to map everything else out. Okay. Because this is the easiest points to draw, right? The left and the right parts of the circle. So this one was your was your epsilon 2, let's call it, and that was 0.0000793. This one was your epsilon 1, which was 0.00221. Okay, right. So that's lying on that x-axis or whatever. So let's draw the original values that were given. So if I was to give you a refresher, these ones, duplicate that. So these were the original values. So here's what you had to do, right? Like in your head, it'd be like, okay, so because this is gamma xy, right? You know that it's paired with x because it's the first subscript, right? So this one goes with this, okay, cool. That means this one, if we were to swap it around, is the negative value, okay? And so these two are a match, and these two are a match, right? When we're plotting. So that means for a positive value, right, going up, we're gonna be plotting epsilon x, okay? And for a negative value, we're going to be plotting epsilon y, okay? So, basically, if I draw it like this, right? Here we have epsilon x is equal to this. Oh, sorry, I should also mention, you also have to see that epsilon x is smaller than epsilon y. So you know on the Mohr circle, it'll be on the left side, and this one will be on the right side. Okay. And this one's mapped with gamma xy, which is 0.001. Cool. So that's how you would map that. This one might go epsilon y is 0.002, and gamma yx is negative 0.001. Okay, cool. All right, so how does this principal axis of rotation thing work? So you have to remember, if you rotate your axis, it's the same direction as Mohr's circle. Okay, but if you rotate your shape, it's opposite direction on Mohr's circle. So here I've drawn it as a rotated shape. Okay, so my shape has gone that way, right? Which means that on the Mohr circle it goes the other way. Okay, so it's basically what's happening in purple here. And the other thing you have to remember is on the Mohr circle, whatever angle you rotate the principal axis by is double what you calculated, right? So this is 2 theta p, right? Which gives 45 degrees, okay? And the last thing we want to, I guess, put in is here. So remember, epsilon is your, what's a good way to call it? Maybe the average? This isn't like a legit term, maybe it's just like epsilon middle, okay? So if I get like this one and this one, for example, and divided by 2, like if I add 0.001 and 0.002, right? And divided by 2, you get this. Yeah. And so that's what I was trying to say over here. Okay. That's the middle of your circle. Okay. In terms of how far up and down, this is the positive value, so we just plot that in. Oh, sorry, I should say gamma max, maybe we'll call it. Okay. Okay, does that make sense? I've got one more example, right? But I can see a few people copying down. I'll just give you like 5 seconds or so. Okay. Okay, sorry, I'm going to move on. Yep, you got a question?
In this example, bro, isn't gamma xy and gamma yx always should be equal opposite?
Wait, say that again, sir?
Gamma xy and gamma yx will be equal opposite always?
Yes.
Isn't the example we just did it like the dB?
Oh, yeah, I see what you're saying.
Is that just something different? Or?
Yeah, that's just something different. Because basically this shape before, I'll exaggerate it, right? So this shape that we had before, right? We had a rectangle and it was like that. And it became a really like wacky rectangle like that. But for our strain elements, they'll have like a symmetrical kind of deformation, right? So, no, but it's like a good point. So basically, if we go back to the strain element, right? Let's call this AB, whatever. And then here, we'll call this D, oh no, actually, well, yeah, I can just show it like this, right? AB, AB, right? So here, if we add these two together, you get, let's just say A plus B is like 0.001 or whatever, right?
Yeah.
But if you get A and B, and it's becoming an obtuse angle, right? It's basically this thing. So yeah, they'll always be equal and opposite, right? Yeah. Okay. Sorry, I think most people have caught up, so I'm gonna move on. So Rosette strain gauges. So a strain gauge is essentially this thing. So one of these is called a strain gauge, right? This is a way to measure your strain, and it records three values. It records these three. Okay, so strain X, strain Y, and shear strain XY. Okay. Now three of them, it's called a rosette. It's like the group term. Okay, so strain rosette is useful for basically obtaining these values. Wait, hold on. Am I cooking too hard? Sorry. Okay, let me take a step back. It doesn't like a strain gauge records one value, right? So this strain gauge would record strain A. This strain gauge would record strain B, and this strain gauge would record strain C. Okay, so they're very dumb. They're like they can only do one thing, and the purpose of it is to record strain in a one-dimensional direction. Okay, so you point it in three different directions, right? It's gonna give you all this information that's gonna let you work out strain X, strain Y, and gamma XY, and yeah, and that might be useful like on a certain point in your structure that's critical that you want to like measure. So like for example, a bridge, you might want to monitor like the health of the bridge to see if it's straining too much before you need to go in and repair it or something like that, right? So it's planted on a single point of a surface on a structure. Okay. All right. So simultaneous equations, right? So this looks nasty, but yeah, I think it's fairly straightforward. Solving the simultaneous equation, I kind of just use MATLAB, I'm gonna lie. And I don't think you really have to solve these by hand. I think so. If this is in your week 4 online test, your block test, like it's online, right? You're allowed to open MATLAB and do all this stuff. So I'm gonna teach you this with the assumption that you don't have to row reduce by hand like a matrix, or like solve like three simultaneous equations by hand. Do you know what I mean? Okay. So I'll just teach you how to set up the matrix, how to punch it into MATLAB, or wait, I said MATLAB, but I meant Symbolab or Wolfram Alpha or whatever. You know, like so there's maths solvers. Okay. I'll just teach you how to like set up the equations. Okay. So. All right, so we're told that a strain rosette, oh, by the way, there's generally two types, the 45-degree ones, and there's one for like 60 degrees, I think. So that's 60 degrees, 60. Sometimes you see this one as well. You might have like that or like that or whatever, right? Doesn't matter. Okay. It's mounted to a surface, and here's the values that it's outputting, basically, right? Okay, so for this one, the first thing you got to keep in mind is that all these angles are measured from. Oh well, actually, you can technically take the datum, I guess you can call it, or like the reference angle from wherever you like, but it's advantageous to take it from here. Okay. So you can think of it like unit circle from high school, right? If you remember, you have your angle like measured counterclockwise or whatever from unit circle. Okay, so that's one way to remember it. So the angle of the strain gauge A is, the one for A is like all the way over here. So it's 45 degrees times 3. The one for B is 90 degrees. And the one for C is 45 degrees. Okay, so just adding 45 each time. All right. Okay. So, give me one sec. All right, great. So basically, if you go onto your calculator and you're back in degrees, okay, if you just type these parts into your calculator. Oh, by the way, if you see cos squared, what you do in the calculator is you can go like cos 135 degrees, but then the squares applied afterwards. So it's as if you're doing cos 135 times cos 135. See what I mean? Okay, So basically that gives you 0.5. That gives you 0.5. These two multiplied by together. So you know how I said before, this is basically like, for example, sine 135 times sine 135. Okay, that's like basically what that squared thing's doing. Here we have sine times 135 multiplied by cos times cos 135. Okay. So if you see that pattern, all right. Cool. So this one's negative 0.5. All right. Next one's for 90 degrees. 0, 1, and 0. And this one, 0.5, 0.5, and 0.5. So this is for 45 degrees, okay? Cool. So basically that gives us these constants, okay? That gives us these constants, and I believe we're told, yeah, sorry, I forgot to mention this, but the question provides us with the amount of strain at each of these gauges, right? So for example, at strain gauge A is negative 200 times 10 to the negative 6, right? So basically, I've set up 3 equations, okay? And what you do is, it's the number that you're provided on the left-hand side of the equation, and then you have to apply this long-ass formula for each of them, okay? So basically, the left-hand side, if you're setting up a matrix, right, the left-hand side goes on the right. What? Okay, yeah, you know what I mean? Like you swap the sides, right? So the left-hand side, we just treat as the right-hand side for the purposes of setting up a mathematical matrix, okay? And it's each of these constants in front of our variable. So if our variable is like epsilon x, right, it's a constant, right, which we calculated, for example, for 1 as 0.5. Right, so you put the constants in for everything, okay? And each row represents an equation, right? So that's 1 equation, that's 2 equation, that's 3 equation, right? That's what you can put in Symbolab, and you can row reduce it, okay? I can show you guys that maybe at the end or something. But yeah, so what that does is, basically, if you remember like first year maths, it just turns the equation, it turns the matrix into something that looks like this: 1, 1, 1, 0, 0, 0, 0, 0, 0, x, y, gamma x, y, which means that having 1 lot of epsilon x, y and 0 lots of these ones gives you this, right? Which means, in other words, x, y, epsilon, I keep saying with the wrong fucking Greek letters. Epsilon x is equal to whatever's on the right-hand side here, okay? Yeah, and then epsilon y is equal to whatever's on the right-hand side here, and then gamma xy is equal to the stuff on the right-hand side here, okay? So row reduces, and then that gives us these. So that's what was on the right-hand side. Okay, the question asks a bit more from us. And I got my friends that's working out because she used to teach this course, right? And I just couldn't be able to rewrite it because she did a good job. But yeah, principal strain, right? So we're doing the same thing. We're just finding the principal strain by getting the average, like average, for example, here and here, middle of circle, that's that. Plus or minus that much gives us that. So you can find max is over here, min's over here. Okay, and yeah, so you can plot the whole thing out. So what she's done, which is actually quite clever, is you can basically make these axes like mapped so that they're times 10 to the negative 6. So instead of getting numbers that are like 0.001, you might call that 100 times 10 to the negative 6, for example, instead. Right. So it just looks nicer because you're writing numbers like 100. I just gave that as an arbitrary example, but like you'd be writing numbers like 380 or something instead of all these decimals all the time, right? Okay, cool. That's pretty much the workshop. What I might do is I might just quickly show you what it looks like on Symbolab. So you might go like this one, matrix. And before we had 3 equations and there was 3 variables, but you have to add one more matrix on the right for to represent the right hand side. Okay, so going back to my numbers, right? We had like 0.5, negative 0.5 is equal to negative 200 times 10 to the 6, whatever. A negative, wait, I think it's negative, yeah. 0, 1, 0, 300 times 10 to the 6, and then 0.5, 0.5, 0.5, 250 times 10 to the negative 6. Okay, and then I think you might have to just say like, actually I think if you just type that, you don't have to write like simplify or solve. I think it just does it. Because it knows that you want to reduce it, and it gives you this basically, right? So those were our answers, right? We basically had this. Oh wait, did I do something wrong? Oh no, you're right. sorry, I heard from that side of the room. Yeah, to the negative 6. Sorry, I thought you meant the negative out here. Yeah, you're right. To the negative 6. Yeah, that looks more right. So that was epsilon x, epsilon y, and gamma xy. Okay. Cool. Does anyone have any questions?
Get that in the final.
No way. No way.
Do we have to do this shit in the final?
I'm pretty sure if you do get assessed on it, you should have access to like Symbolab or whatever. So I think you only get assessed on the strain gauge, like simultaneous equation stuff for this test, maybe.
Right.
Yeah.
So we can do the test from like home, right?
Yeah, double check with Alina, but I'm pretty sure, yeah. It's not like NSPER or anything. It's just you just do it. There's a time where you have to like sit down and do it, and then you just do it.
Can you use like ChatGPT?
Probably, but I don't know. I feel like ChatGPT performs pretty badly for solid mechanics.
Yeah.
So you can, but like I wouldn't recommend it.